somewhere around 70,000 years ago, on a night that looked like any other night, humanity came breathtakingly close to simply stopping. No monument marks the moment, no memory of it survived. The people alive then had no way of knowing that their species had been reduced to something so small, so fragile, that a single bad season, a single unlucky disease, a single shift in the wind could have erased every human being from the face of the earth forever. And yet here you are listening to this, which means somehow against odds that would make any statistician shake their head, somebody made it through. That is the mystery at the centre of this story. If you're using this to fall asleep tonight, that's exactly what it's here for. So before we go any further, drop a comment and tell me where you are and what time it is. I love reading them. It's always Tokyo at midnight, sitting next to Sydney at 2 in the morning, sitting next to someone in Toronto who just can't turn their brain off. Wherever you are, you're in good company. And if you want to listen without any interruptions, you can follow the show on Spotify, completely ad-free, completely music-free, just the story. The link is in the description, and it genuinely helps keep this going. Now, back to 70,000 years ago. Geneticists, anthropologists, and archaeologists have spent decades piecing together evidence that our species passed through what they call a bottleneck, a period during which the total number of humans alive on Earth may have collapsed to somewhere between a few hundred and a few thousand breeding individuals. Some estimates put the number as low as around 10,000 people. Others suggest it could have been even smaller than that, perhaps dramatically smaller. The exact figure is still being debated, which is part of what makes this story so haunting. We're not entirely sure how close the edge was. We just know we got very close to it. A bottleneck in the language of population genetics is exactly what it sounds like. Imagine a bottle. When you pour liquid through it, the narrow neck restricts the flow. Whatever gets through carries only a fraction of what was in the wider part above. When a population crashes and then recovers, the survivors carry only a fraction of the genetic diversity that existed before. They become the narrow neck, and everything that comes after, every human alive today, pours through them. The richness, the variation, the countless small genetic differences that had accumulated over hundreds of thousands of years of human evolution, most of that is gone, filtered out, lost forever in whatever catastrophe caused the crash. And the evidence that something like this happened is actually written inside every one of us. Human beings are, genetically speaking, remarkably similar to one another. Astonishingly so when you compare us to other species. 2 chimpanzees living in the same forest carry more genetic variation between them than you do, compared to someone picked at random from the other side of the planet. That is deeply strange if you think about it. We're spread across every continent. We've been evolving for hundreds of thousands of years. We should be far more diverse than we are. The fact that we're not is the fingerprint of a bottleneck. Something happened that squeezed us down, that reduced us to a small founding population from which all 8 billion of us eventually descended. But what? That's where the story becomes genuinely unsolved in the most fascinating way. There are several suspects, and none of them are fully cleared. The most dramatic is a supervolcano. Around 74,000 years ago, a massive eruption occurred at a place called Toba on the island of Sumatra in what is now Indonesia. By most estimates, it was the largest volcanic eruption in the last 2 million years. The kind of eruption that doesn't just reshape a landscape but potentially changes the climate of the entire planet. Ash layers from Toba have been found thousands of miles away, across South Asia, across East Africa, drifting through ice cores drilled from Greenland. Some researchers believe this eruption triggered a volcanic winter, a prolonged cooling of global temperatures that devastated plant life, disrupted food chains, and pushed already struggling human populations to the very edge of survival. But Toba is not the only suspect, and it may not even be the primary one. Climate volatility in general, was making life extraordinarily difficult during this period. The world was cycling in and out of glacial conditions. Sea levels rose and fell, forests shrank, grasslands shifted. The landscapes that early humans had learned to read and navigate were rewriting themselves, sometimes faster than populations could adapt. And then there is disease, an invisible suspect that leaves almost no trace in the fossil record, but can hollow out a species with terrifying efficiency. Ecological pressures, competition with other hominin groups, shrinking habitats, the simple grinding difficulty of survival in a world that was changing faster than anyone could keep up with. All of these were probably involved in some combination. The exact proportion is something scientists are still working out. What we can say with a reasonable degree of confidence is that somewhere around 70,000 years ago, the human story nearly ended before it really began. The technology that would eventually build cities and send signals to distant stars, the language that would carry stories from one generation to the next, the art, the music, the accumulation of everything we call civilization, all of it was nearly extinguished by something we still don't fully understand. And that tension, that not fully knowing, is part of what makes this worth staying awake for, or in your case, worth drifting off to. Over the next while, we're going to move through this period carefully. We'll look at what the DNA actually shows, what the archaeological record does and doesn't tell us, what Toba may or may not have done, and how a small, scattered group of humans found ways to hold on when every pressure in the environment was pointing toward extinction. We'll look at the refuges where people may have sheltered, the behaviours that may have saved them, and what the experience of near extinction might have done to shape who we eventually became. The story of how humanity survived is also quietly the story of why we are the way we are. And it starts on a night when almost nobody made it through. So let's slow down for a moment and make sure we're speaking the same language, because scientists use the word bottleneck in a very specific way, and understanding what they actually mean by it changes how you see the evidence, how you weigh the uncertainty, and how you appreciate just how strange and improbable our survival really was. Start with the simplest version. A population bottleneck is any event or period during which the size of a population drops sharply, and then, if the species is lucky, recovers. That's it at the most basic level. Numbers go down. Numbers come back up. But in between those two moments, something irreversible happens. Genetic diversity gets lost. And unlike a burned forest that eventually grows back from seeds, the diversity that vanishes during a bottleneck doesn't return on its own. It's gone. The genetic possibilities that existed in the population before the crash, all the variation that had been building across thousands of generations, much of it simply disappears with the individuals who didn't survive. There's a related concept called the founder effect, which is worth knowing because it often gets tangled up with bottleneck discussions. The founder effect happens when a small group breaks away from a larger population and establishes itself somewhere new. The founding group carries only a slice of the original genetic diversity, and everything that comes after them inherits only that slice. It's less about catastrophe and more about isolation. But the result looks similar. A smaller genetic toolkit, reduced variation, a population that, to a geneticist reading its DNA thousands of years later, looks like it came through a narrow door. Now here's where it gets a little more technical, but stick with it, because this distinction matters enormously for understanding how scientists date and measure what happened to us. When researchers talk about population size in this context, they're usually not talking about the raw number of people alive at any given moment. That's called the census population, the simple head count. What geneticists are usually measuring is something different. They call it the effective population size, often written as NE. The effective population size is essentially the number of individuals who are actually contributing genes to future generations, who is actually breeding successfully, who is passing their DNA forward into the next generation, and the one after that. These two numbers can be very different. Imagine a group of 1,000 people, but only 100 of them are of reproductive age. Only half of those are finding partners, and those partnerships are unequally distributed so that a few individuals, father or mother, a disproportionate number of children. Your census population is 1,000, but your effective population size might be closer to a few hundred or even less. The genetic legacy of those people, what eventually gets carried forward in time, reflects the effective population, not the census count. This is why genetic estimates of the human bottleneck tend to look so dramatic. Researchers aren't necessarily saying there were only 1,000 humans alive in absolute terms. They're saying the effective breeding population, the group whose genes actually shaped all of us, may have been that small, and bottlenecks leave signatures. Very specific, readable signatures in the genome. When a population crashes and rebuilds itself from a small founding group, the variation in certain regions of the DNA compresses. Rare gene variants that existed before the crash simply vanish because they happen to be absent in the survivors. What remains is a population where individuals share much more DNA than you'd expect given how long the species has been around. That shared similarity, that genetic sameness, is the fingerprint scientists look for. And in humans, that fingerprint is unusually clear, disturbingly clear, if you spend too long thinking about what it implies. One more distinction worth drawing. Bottlenecks don't have to be global. A population can crash in one region while surviving comfortably in another. A drought that devastates one group might never touch a group 500 miles away near a different water source. This creates regional bottlenecks, local crashes that leave their own genetic signatures in the populations that later descend from survivors of that area. Some of what we read in ancient DNA might reflect these localized collapses rather than a single catastrophic worldwide crash. This is part of why reconstructing what happened is so genuinely difficult. The signal we're reading could be the echo of one enormous event, or it could be the overlapping echoes of multiple smaller catastrophes accumulating over a long stretch of time. Which brings us to the problem of prolonged bottlenecks. Most people imagine a bottleneck as a single sharp moment. Population crashes, stays low briefly, then recovers. But bottlenecks can last for thousands of years. The population might stay depressed for dozens of generations, never quite recovering before the next crisis hits, slowly losing diversity across an extended period of stress rather than a single dramatic blow. Some researchers think the human bottleneck wasn't a sudden collapse at all, but a long grinding period of low population size spread across tens of thousands of years. If that's true, it makes the story even more difficult to unravel because you're not looking for one event to explain it. You're looking at an era of cumulative pressure from which our ancestors barely managed to emerge, and pinning down the timing is its own challenge. Genetic methods for estimating when a bottleneck occurred rely on rates of mutation, on statistical models, on assumptions about generation lengths and breeding patterns that can shift the estimated dates by tens of thousands of years in either direction. Different research groups using different methods and different assumptions have arrived at different estimates. Some place the deepest point of the human bottleneck around 70,000 years ago. Others suggest an earlier or later date. Some genetic analyses point to a bottleneck beginning much further back and lasting far longer than previously thought. The number 70,000 is useful because it roughly aligns with other evidence from geology and archaeology, but it shouldn't be treated as a precise timestamp. It's more like a general address than a specific location. What is consistent across virtually all of these analyses is the conclusion that something happened, something real, something that compressed the genetic diversity of every human being alive today into a range that is, by any biological measure, surprisingly narrow. We are all, in a meaningful genetic sense, close relatives. The breadth of human variation that should exist after hundreds of thousands of years of evolution across a wide continent is simply missing. That absence is a story. The question we're trying to answer is what wrote it. And to understand that, we need to go back to the world itself. The physical world that our ancestors were living in when the pressure began to build. To do that, we have to step outside the numbers and models and imagine the planet itself. Not the modern world with its crowded cities and glowing maps, but Earth as it was in the late Pleistocene, in the middle of one of the great ice ages. If you could have seen it from space, the first thing you'd notice is the ice. Huge sheets of it draped over North America and Northern Europe, kilometers thick in places, pressing continents down under their weight. Glaciers spilling out of mountain ranges, grinding rock into powder. Sea levels far lower than today, shorelines pushed outward, continental shelves exposed as wide, cold plains. But our story doesn't take place on those ice sheets. It takes place mostly in Africa, thousands of kilometers to the south, where the world looked very different and yet was still deeply shaped by that distant cold. Because ice ages aren't just about ice. They're about how the entire climate system rearranges itself. Where heat goes, where rain falls, how winds move. When those giant ice sheets grow in the north, they change the way air and ocean currents circulate. They tug the tropics around like a vast, slow lever. In Africa, that meant the rain belts, the great seasonal migrations of storms that today feed the savannas and forests, didn't sit still. They shifted north and south over thousands of years, sometimes bringing generous monsoons deep into the continent, sometimes pulling moisture away and leaving only dust and wind behind. Imagine the Sahara, which you probably picture now as endless dunes and blazing heat. 70,000 years ago, it wasn't locked into one identity. Over long cycles it breathed. In wetter phases, the desert could become a patchwork of grasslands, lakes and rivers, what scientists call green corridors stretching across what is now deadly dry terrain. Hippos in lakes, crocodiles in rivers, herds of antelope, maybe even humans, moving through habitats that feel nothing like our modern picture of the Sahara at all. Then the climate would shift again, the rains would retreat, lakes would shrink to puddles and then to salt flats, rivers would break into isolated pools and finally vanish. The green corridors would close, replaced by blowing sand and bare rock. What had been a highway for animals and people became a barrier almost impossible to cross. These weren't smooth changes, they came in pulses. The late Pleistocene was governed by glacial-interglacial rhythms, long swings in climate driven by subtle changes in Earth's orbit and tilt. Over tens of thousands of years, ice sheets grew, then partially melted, then grew again. Each phase shifted the balance of temperature and rainfall worldwide. Layered on top of these slow rhythms were abrupt events that arrived much faster. Abrupt in climate science can still mean decades or centuries, but from the perspective of a human lifetime, that's fast enough to matter. A couple of bad years, and a child born in a green, well-watered world might reach old age under skies that almost never rained. Ocean circulation can stall or reroute. Dust from drying continents can cool the atmosphere. Monsoon systems can weaken or suddenly jump to a new position. In the Greenland ice cores, these switches show up as sharp steps in temperature, 5, 6, even 10 degrees of change in what looks like a geological heartbeat. Africa felt the echo of those northern jumps in the form of rainfall flickering on and off. So when we say the world around 70,000 years ago, we're talking about a planet in one of these unstable phases. Ice sheets large but not at their maximum, sea levels low, Africa cut into zones by moving climate lines, some regions relatively green, with savanna and woodland and reliable rivers, others drifting toward hyper-aridity, expanding deserts, vanishing lakes, long stretches of scrub where large animals struggled to find enough to eat. For humans living then, this instability wasn't an abstract pattern. It was whether there was water in the next valley, whether the migratory herds still passed through at the expected time, whether a familiar trail to a neighbouring group was now blocked by a newly formed desert or a swollen river. Food, water, and mobility were tied together in ways that are easy to overlook now. If the rains failed for a few years in a row, rivers shrank and fish died off. Grazing animals lost weight, stopped breeding, or migrated away. Plants produced fewer seeds, fewer fruits, fewer tubers. A landscape that could support, say, 100 people one decade might barely support 30 the next. When populations are small, those fluctuations are dangerous. A large, widespread species can absorb bad years in one region because other regions do better. But if you're living in scattered bands, thinly spread across a continent where the green zones are narrow and shifting, a modest climate wobble can look like the end of the world. A lake that retreats by a few kilometres doesn't just move the shoreline. It removes a predictable water source, fishing ground and meeting place. A rainfall belt shifting a few hundred kilometres north can turn a usable corridor into a lethal barrier. It might close off contact with distant kin. It might trap a group between desert and ocean. It might mean that the next generation of children has to grow up walking far longer for firewood and water, expending precious energy simply to survive. In that kind of world, mobility is both salvation and risk. You move to follow the rains and the herds. You move to escape drought and competition. But moving means crossing unfamiliar territory, where other groups may already be clinging to marginal resources, where predators hunt, where you don't know the seasonal patterns. Sometimes a shift in climate opened opportunities. A temporary green corridor could let people explore new regions, discover new water holes, new sources of stone, new plant foods. But those windows didn't stay open forever. A group that bet on a new route might find it closing behind them, cut off from their old homeland by newly hostile terrain. The archaeological record from this period hints at exactly this kind of stop-and-go pattern. Layers showing lakes full, fish bones abundant, tools left on comfortable shorelines. Then layers of dust, fewer artifacts, evidence of abandonment. People were moving with the climate, chasing the patchy, shifting zones where life was possible. All of this matters for our bottleneck story, because it shows how many different ways pressure could build. You don't need a single planet-wide catastrophe to push a species toward the edge. In a world governed by glacial, interglacial cycles and abrupt climate jolts, a series of small, regional crises could do the job just as well. A rain belt nudging south here, an inland lake disappearing there, a green corridor closing for a few centuries. Each of those changes might reduce the safe habitat available to humans, concentrate them into fewer refuges, fragment their networks, and make long-distance exchange harder. Fewer contacts mean fewer mating partners. Fewer mating partners mean lower effective population size, even if the total number of bodies isn't yet critically low. In that sense, the late Pleistocene climate turned the entire African landscape into a kind of moving maze. Paths open, paths close. Resources pulse on and off like flickering lights. Our ancestors were navigating that maze with stone tools, fire, memory, and social ties, nothing more. When a species is already small and scattered, the difference between a good century and a bad one can echo for tens of thousands of years in its DNA. A slight contraction of habitable land, a brief tightening of the rainfall belt, a few generations of poor survival. Those little stresses repeated across regions and times are exactly the kind of pressures that can carve a bottleneck shape into the genome. To see how scientists read that shape, how they turn the faint genetic traces of these long-vanished climates into a narrative of near extinction, we have to leave the ancient skies and follow the evidence into the double helix itself. When geneticists talk about a bottleneck 70,000 years ago, they're not just guessing. They're reading patterns written into our DNA, patterns that only make sense if, at some point, there were far fewer of us than there are today. The first clues came from some of the simplest parts of our genome, the pieces that only travel down one line of ancestry. One of those is mitochondrial DNA, or mtDNA. It sits inside the little energy factories in your cells, and you inherit it only from your mother. Your mother got hers from her mother, and so on in an unbroken line stretching back through time. Because mtDNA doesn't shuffle with each generation the way most of your DNA does, it acts like a slowly mutating clock on a single branch of your family tree. Mutations accumulate at more or less regular intervals. When scientists compare mtDNA from people all over the world, they can see which lineages are closely related, which split long ago and roughly when different branches converge on a common ancestress. Do that for enough people, and something striking appears. All human mtDNA lineages living today eventually trace back to a woman who lived in Africa hundreds of thousands of years ago. She wasn't the only woman alive, or the only ancestor we have from that time. She's just the one whose mitochondrial line survived. Others ended when daughters weren't born, or when lineages simply died out. Yet the mtDNA tree doesn't look like one from a species that was always numerous and widespread. It has long, thin branches and signs of pruning. There are missing offshoots, gaps where diversity should be. When researchers model how that pattern would form, it fits better with a population that shrank dramatically, and then regrew, than with one that stayed large and steady. The second line of evidence comes from the Y chromosome, the stretch of DNA passed down from father to son. Like mtDNA, it mostly escapes the genetic shuffling that mixes up the rest of the genome each generation. That makes it another kind of timekeeper, but this one runs along the paternal line. When scientists build a family tree of Y chromosomes around the world, they see a similar story, a common origin in Africa, branches splitting and spreading, and again, signs that the tree was once very narrow. Many potential branches seem to have been clipped early on. Only a few male lineages made it through certain stretches of prehistory. mtDNA and Y chromosome data alone can't prove a bottleneck. They're just two thin threads through the vast fabric of ancestry. So researchers turn to the rest of the genome, the autosomes, the 22 pairs of chromosomes you get half from your mother and half from your father. Autosomal DNA is messier. It recombines. It's shuffled and redealt every generation. But that very messiness contains a record of how many ancestors you had at different points in time, and how similar or different they were from each other. The basic idea is this: in a large, stable population, you expect a lot of genetic variation. Many different versions of genes, many combinations of those versions, and plenty of rare variants that persist for a long time. In a small population, by contrast, chance matters more. Random events can erase rare variants quickly. Certain gene versions can become common simply because there aren't many individuals to dilute them. If you look closely enough at the genome, you can see traces of these processes, long stretches where everyone shares the same sequence, patterns of how often particular variants occur, the length and arrangement of chunks of DNA inherited together. These are the kinds of clues that coalescent models use. Coalescent theory works backwards. Instead of starting with an ancient population and moving forward through time, it starts with living genomes and asks, if we trace each segment of DNA back through parents and grandparents and great-grandparents, how long does it take before two people's sequences coalesce into a shared ancestor? In a small ancestral population, those common ancestors lie closer in time. There are fewer individuals to pass on distinct versions of the sequence, so lineages merge quickly. In a large population, lineages can stay separate for longer, tracing back through many more generations before they meet. So researchers take the DNA of many modern humans, feed it into mathematical models based on coalescent theory, and ask, what sizes of ancestral population best explain the patterns we see today? How big would the population have to be, at different points in time, to generate this particular mix of shared and unique genetic variants. Run those simulations often enough with different assumptions, and a broad picture emerges. It's not a single line, more like a band of possibilities, but the band narrows at certain times. Around the period roughly 800,000 to 900,000 years ago, and again closer to 70,000 years ago, many models show effective population sizes dropping sharply, then rising again. Effective population size is an important word here. It doesn't mean how many people you could have counted on the ground with a clipboard. It means how many individuals, in genetic terms, were actually contributing their DNA to the next generation in a way we can still detect. A species might have, say, 20,000 bodies alive at a given time. But if most of the breeding is happening within a few clustered groups, the effective population size can be much smaller. Most genetic studies agree on some core themes. Our species went through periods when genetic diversity was squeezed, consistent with bottlenecks. Africa holds the deepest and widest branches of our family tree, supporting the idea that our origins lie there. And non-African populations have a subset of that variation, reflecting an expansion out of Africa from a relatively small founding group. But the details are where things get fuzzy, and sometimes contentious. Different studies disagree on just how small the population may have gotten, and exactly when. Some models suggest an extreme bottleneck around 800,000, 900,000 years ago, with effective sizes possibly in the low thousands or less, lasting a very long time. Others find a more modest constriction, or place stronger bottlenecks at different moments, like the one tied to the migration out of Africa roughly 60,000 to 70,000 years ago. Even when studies broadly agree that there was a serious narrowing of our lineage, the confidence intervals are wide. One analysis might say fewer than 10,000 breeding individuals. Another, using different assumptions, might propose fewer than 2,000. Both see the same general shape in the data, a steep valley in the curve of population size over time, but they draw the valley's depth and width differently. Part of the uncertainty comes from one simple problem: mutation rates. To translate genetic differences into years, you need to know how often mutations occur. Do they happen on average once every few dozen generations at a given spot? Once every few hundred? The answer can shift depending on how you estimate it, by counting differences between parents and children today, by comparing humans to other primates, or by using fossils to calibrate the clock. Tiny changes in the assumed mutation rate ripple out into big differences in the dates you assign to past events. A slightly faster clock pushes coalescent times closer to the present. A slower clock drags them back in time. So when you hear that a bottleneck happened about 70,000 years ago, or about 800,000 years ago, that about hides a wide range of possibilities. Sampling bias is another problem. Much of modern genetics is based on people who are easier to study. Populations living in accessible regions, populations with existing medical data, populations with the infrastructure to participate in large-scale research. Many groups remain underrepresented, especially in parts of Africa, where some of the most informative diversity is likely to be found. If you miss important branches of the family tree, your picture of its shape can be distorted. It might look like all the surviving lineages passed through a single narrow bottleneck, when in fact some unsampled lineages had slightly different histories. On top of that, coalescent models always make assumptions about how populations were structured. Did people mate randomly across a wide area, or mostly within small local groups? Were there steady migrations between regions, or only occasional contact? Did certain lineages have more children than others? Each choice changes how quickly genetic lineages merge as you travel backward in time. So genetics can point strongly toward a history of bottlenecks and expansions, but it can't, by itself, tell us exactly what caused them or exactly how many individuals were alive in each generation. It can't say there were precisely 1,280 humans huddled by a certain lake in Africa, and a volcano almost killed them all. DNA doesn't carry that level of narrative detail. What it can do is set boundaries. It can say something happened that reduced diversity to this degree. Any scenario we propose, volcanic winters, shifting rain belts, diseases, competition with other species, has to be consistent with those genetic constraints. It can also show us relative timings, that certain squeezes happened before others, that expansions followed, that our lineage was never a smooth, gradual growth, but a series of rises and falls, to turn those shadowy genetic shapes into a concrete story about climate, volcanoes, and human survival. We have to bring in another kind of evidence entirely: stones, bones, and layers of earth. And when we do, we run into a different kind of problem, the problem of silence. If DNA is like a blurred graph of our past, archaeology is more like listening to distant echoes in a canyon and trying to reconstruct the conversation. Instead of genes, archaeologists work with things people left behind: stone tools, animal bones, bits of charcoal, occasional fragments of shelter or hearth. The logic is simple enough. More people on average leave more stuff. A landscape that holds many occupation sites from a certain period, camps, kill sites, workshop areas, caves filled with layers of debris, probably supported more humans than a landscape with only a handful of traces. So researchers count. They map how many sites show up in different time slices. They compare tool traditions, how complex they are, how standardized, how widely they spread. They look at how often hearths appear, how thick the garbage layers become, whether certain animals are hunted more intensively over time. A jump in the number of sites or a spread of similar tools over a wider area might hint at population growth. A long, quiet stretch in the record, few sites, fewer tools, less variation, might hint at a decline. But the key word here is might, because archaeological evidence is not a complete recording of the past. It's a patchwork assembled from what happened to survive, in places that happen to be excavated, by people asking certain kinds of questions. There are whole continents of silence in between the points we can see. Stone tools are our luckiest artifacts, because stone lasts. But even stone only preserves where the conditions are right, and where people happen to use it. Organic tools, wood, fibre, leather, plant baskets, even bone in many climates, simply vanish. If a group of hunter-gatherers spent most of their time making wooden spears, weaving nets, and collecting shellfish with their bare hands, they might leave almost nothing we can detect after tens of thousands of years. Archaeology would mishear them as a whisper, even if they were, in their time, a loud, thriving community. That's preservation bias. Some materials, some environments, some kinds of behaviour get recorded much more than others. Rock shelters and caves preserve better than open-air camps. Dry caves and cold sites can freeze time for us. Tropical forests and acidic soils erase almost everything. Coastal sites can be spectacular when they survive, but many shorelines from the last glacial cycles are now drowned, lying under meters of seawater on continental shelves. So when you look at a graph of number of sites over time, it's not just population that's changing. It's also sea level erosion, how much land has been surveyed by archaeologists, how brightly certain traditions show up in stone. This is the problem of silence. When the record goes quiet, we can't tell immediately whether people were gone, or just living in ways that left fewer traces in places we haven't yet found. This matters a lot for the story of a bottleneck around 70,000 years ago. If there really was a dramatic reduction in human numbers, we might expect it to show up in Africa's archaeological record around that period. Fewer sites, simpler tools, broken continuity between older and younger layers. In some places we do see changes. In others we see something more surprising: continuity. Take Eastern and Southern Africa, regions that hold some of the richest Middle Stone Age records. Sites like Pinnacle Point and Claysees River on the South African coast, and others like Blombos, Sibudu and Border Cave, preserve long sequences of occupation stretching across the crucial window between roughly 100,000 and 50,000 years ago. At these coastal sites, people were collecting shellfish, catching fish, gathering seaweed, and combining those coastal foods with terrestrial hunting and plant gathering. In some layers, there is evidence of heat-treating stone to improve its flaking properties, using pigments like ochre, shaping bone tools, and even creating engraved pieces that look to us like early attempts at symbolism or decoration. Crucially, many of these sequences don't just stop around 70,000 years ago. They show people there before, during, and after the time when a bottleneck is often proposed. The tool traditions change, but they change gradually. There is no obvious, universal break where everything collapses and then restarts from scratch. Interior sites in Africa tell a more varied story. In some inland regions, there appear to be gaps in the record, fewer known sites, thinner deposits, around the same broad time frame. In others, we see what looks like a shift in technologies, new kinds of points, different raw materials, different hunting patterns. Interpreting this is tricky. Does a gap mean people really left or died out in that area? Or that their campsites were ephemeral and didn't preserve well? Does a change in tools mean a new population moving in, or the same people adapting to new conditions? Archaeologists try to answer these questions by looking for continuity in small details. Do particular tool-making techniques persist across the supposed gap? Do local raw materials stay the same? Are there shared habits in how hearths are built, or how bones are broken for marrow? When those fine-grained signatures continue, even as climate shifts or big eruptions occur, it suggests that at least some local populations persisted through the crisis. They may have been squeezed, they may have moved around, but they weren't wholly replaced. When the signatures vanish and a quite different tradition appears later, it might point to local extinctions and recolonizations, patterns that would fit a metapopulation world where some groups fail and are later replaced by migrants from refuges. One revealing contrast comes from comparing coastal and interior records. Along the South African coast, the archaeological signal around 70,000 years ago often looks relatively steady. People continue to exploit marine resources, sometimes intensifying their use of shellfish and fish. This has led some researchers to propose that coastal zones acted as refuges during harsh inland droughts, offering reliable food from the sea when rainfall patterns failed. Inland, especially in drier parts of eastern and southern Africa, the site record sometimes thins out or shifts, hinting that life away from coasts might have become much more precarious. If overall populations were shrinking, coasts could have become crowded lifelines, narrow strips where many of the surviving groups clustered. Seen in this way, archaeology begins to line up with the genetic story, but not in a simple one-to-one way. Genetics tells us that, globally, effective population sizes shrank. Archaeology shows us that locally, some places retained continuous occupation while others flickered on and off. Genetics suggests a long-term squeeze on diversity. Archaeology reveals pockets of technological innovation and cultural resilience right in the midst of that squeeze. Sometimes the two lines of evidence seem to point in the same direction. A thinning archaeological record in a region, paired with signs of reduced genetic variation today, makes a bottleneck there more plausible. Sometimes they complicate each other. Rich, continuous archaeological sequences through a supposed bottleneck period forced geneticists to think in terms of structured populations, many small groups, some doing relatively well in refuges, even as the species as a whole contracts. And sometimes the silence in the ground doesn't match the curves in the DNA at all. That mismatch doesn't mean one of them is wrong. It usually means our picture is still incomplete, that sites remain undiscovered, that underwater landscapes are hiding ancient camps, that models need to account for more complex patterns of survival and movement. So as we move closer to the story of the Toba eruption and the dramatic idea of a volcanic winter nearly wiping us out, we have to keep that tension in mind. Genetics can hint that something drastic happened. Archaeology can show us how, where, and whether people on the ground actually suffered, adapted, or endured. To understand whether a single supervolcano really came close to finishing us, we need to listen carefully to both, to the quiet language of stones and ash, and to the faint patterns in our blood. Around the time our genetic graphs start to dip and wobble, something else happened on Earth. Something so enormous that, for a while, some scientists thought it might explain almost everything. It happened in what is now Indonesia, on the island of Sumatra, about 74,000 years ago. If you could have stood there beforehand, you would have seen a vast volcanic mountain, part of the restless ring of fire that circles the Pacific. Beneath it, for hundreds of thousands of years, magma had been rising, cooling a little, rising again, building a reservoir of molten rock, gas, and pressure. Then, one day in that deep past, the system lost its balance. Toba erupted. Not a gentle cone eruption, not even a Mount St. Helens or a Vesuvius. A supereruption. One of the largest volcanic explosions our species has ever overlapped with, and one of the biggest the planet has seen in the last couple of million years. Geologists estimate that Toba ejected on the order of 2,800 to 3,000 cubic kilometers of material. Numbers like that are hard to visualize. Imagine scraping off a layer of rock several meters thick from an area the size of a small continent. That's the approximate scale of matter ripped out of the earth and blasted into the sky. Ash rained down across South Asia. In parts of India, Pakistan, and the Indian Ocean, layers of volcanic ash, many centimeters thick, in some places tens of centimeters, settled onto the ground, later buried and preserved for us to find. In the middle of the old volcanic edifice, the emptied magma chamber collapsed, leaving behind a vast caldera tens of kilometers wide. Today it's filled with water, a serene lake occupying the scar of one of the most violent days in recent geological history. Events like this don't just affect the local scenery. They reach for the sky, along with ash and pumice. Toba pumped huge quantities of volcanic gases into the upper atmosphere: sulfur dioxide, water vapor, carbon dioxide, and a cocktail of other compounds. Of these, sulfur dioxide is the crucial player in the story that comes next. High in the stratosphere, sulfur dioxide can react with water vapor to form tiny droplets of sulfuric acid. These are volcanic aerosols, minuscule particles suspended high above the weather, forming a thin, hazy veil around the planet. Aerosols are very good at one thing: they reflect sunlight. They scatter incoming solar radiation back into space before it ever reaches the surface. Less sunlight means less energy to warm the ground and the oceans. The result is a temporary cooling, a kind of artificial, short-lived shade cast over the entire Earth. We've seen this happen in recent history on a much smaller scale. The 1991 eruption of Mount Pinatubo in the Philippines lofted enough sulfur into the stratosphere to cool global average temperatures by about 0.5 degrees Celsius for a year or two. Crops were affected, weather patterns shifted, satellites recorded the change. Now take that idea and turn the volume up many, many times. The Toba catastrophe hypothesis proposes that the aerosols from this supereruption were so abundant and persisted for long enough that they triggered a volcanic winter. According to the dramatic version of this scenario, global temperatures might have dropped several degrees for years, maybe a decade or more, on top of an already unstable ice age climate. Under this view, the sky would have been dimmer. Growing seasons would have shortened. Monsoon systems might have weakened or shifted. Plants stressed by cold and low light would have produced less food. Animals depending on those plants, and on other animals in turn, would have suffered cascading declines. and humans already living in scattered, vulnerable groups would have been pushed into an even narrower corner of survival. This is where Toba and the genetic bottleneck meet. In the late 1990s and early 2000s, some researchers noticed that the estimated timing of a severe reduction in human effective population size, somewhere in the broad window around 100,000 to 50,000 years ago, overlapped roughly with the 74,000-year age of the Toba eruption. At the same time, geologists and paleoclimatologists were emphasizing just how large Toba had been, and modeling studies suggested that a supereruption of this scale might, in theory, produce dramatic, long-lasting cooling. It was tempting to connect the dots. The proposed story went something like this. Before Toba, humans were already dealing with Ice Age fluctuations, but populations were larger and more widespread. Then Toba exploded, shrouding the globe in aerosols. Temperatures plunged, rainfall patterns shifted, plant communities crashed, animal populations dwindled, human groups across Africa and Asia, facing a sudden, severe downturn, died off in large numbers. Only a small fraction survived, perhaps in a few geographically lucky refuges, where the climate impact was less extreme, or where food resources were buffered along coasts, in sheltered highlands near persistent freshwater. In this scenario, the genetic bottleneck is the fingerprint of that disaster. The reason we see such low diversity in certain parts of our genome is that most lineages vanished in the aftermath of Toba's volcanic winter. The 1,000 or so effective ancestors reconstructed by geneticists would then represent the survivors of that singular catastrophe, the ones who managed to hold on until the aerosols thinned, the sunlight returned, and ecosystems slowly recovered. It's a powerful cinematic hypothesis. A single day or sequence of days in Sumatra setting off a chain reaction that nearly ends our story worldwide. A plume of ash and gas rising into the sky, dimming the sun, cutting down forests, emptying savannas, forcing our species through a narrow evolutionary doorway. But power and drama are not the same as certainty. Today, researchers are more cautious about giving Toba the starring role in our near-extinction story. Some climate models suggest the cooling might have been more moderate than once thought, or shorter-lived. Paleoclimate records, like ice cores and lake sediments, show changes around this time, but not always the kind of catastrophic, synchronized crash that the most apocalyptic versions of the hypothesis would predict. So how would we decide if Toba really was the trigger for a human bottleneck? The supporting evidence would need to align along several lines. In climate archives, we would expect to see a clear, sharp global signal of cooling and environmental stress right after the Toba ash layer, drops in temperature proxies, shifts in rainfall indicators, evidence of ecosystem disruption. In animal records, we might look for sudden declines in populations, changes in species ranges, or extinctions clustering around the same time. In the archaeological record, we might expect widespread site abandonment or sharp breaks in cultural traditions across Africa and Asia. Tool industries might disappear or simplify abruptly. Long-occupied caves might have layers that stop around the ash horizon and only restart much later, suggesting local extinctions and delayed recolonization. In genetics, we would look for evidence that the most severe contraction in human effective population size lines up closely with 74,000 years ago, and that the pattern fits a relatively short, sharp downturn rather than a long, drawn-out squeeze. On the other hand, certain findings would undermine the idea that Toba nearly wiped us out, or that it was the main driver of the bottleneck. If we see continuous occupation at many sites spanning the Toba ash, with no sign of demographic collapse, that weakens the catastrophe narrative. If climate records show only modest or regional cooling rather than a global decade-long volcanic winter, the environmental pressure on humans might have been significant, but not annihilating. If genetic reconstructions place the bottleneck earlier, later, or spread over tens of thousands of years, then a single eruption begins to look less like the cause and more like one episode in a much longer saga of stress. In the next sections, we'll look at those lines of evidence one by one: the ash in South Asia, the refuges in Africa, the climate records, and see how well they match the picture of a world plunged into sudden darkness by Toba's roar. Only then can we decide whether that mountain in Sumatra really brought us to the edge, or whether it was just one more hammer in a world already full of blows. To answer that, we have to leave the human story for a moment and listen to the planet itself. Earth keeps a diary, not in words but in layers. Far to the north and south, in Greenland and Antarctica, snow has been falling for hundreds of thousands of years. Each winter's snow compresses into the previous years, slowly turning to ice. Tiny bubbles of ancient air get trapped inside. Dust, ash, sea salt, even pollution from distant volcanoes settle into those layers. Drill down through that ice and you're travelling backward through time, year by year, storm by storm. When scientists look at these ice cores, they measure several things at once. They look for physical layers of ash and sulfate that might mark big eruptions. They measure ratios of oxygen and hydrogen isotopes that act as thermometers, telling us how cold the air was when that snow fell. They examine trapped gases and trace chemicals like a forensic team reading clues from a crime scene. Around the time Toba erupted, those cores do show changes. There are signals of volcanic sulfate in some records, and there are fluctuations in temperature proxies. But the pattern is complicated. If Toba had plunged the world into a deep, decade-long volcanic winter, we might expect a sharp, unmistakable drop in these temperature proxies right after the eruption, lasting for years, perhaps with signs of unusual dryness or disrupted atmospheric circulation. What we actually see is more subtle. There are cool spells, but they sit on top of an already noisy Ice Age climate, full of its own ups and downs. Some cores show a cooling that could be consistent with a significant eruption. Others show smaller blips or variations that are hard to distinguish from the background climate swings already in motion. Ice is only one part of Earth's diary. Lakes and oceans keep their own records. On the bottoms of lakes in Africa, India and elsewhere, thin layers of mud and organic material settle year after year. In the ocean, shells of microscopic plankton rain down to the seafloor, building up sediments that reflect the chemistry and temperature of the water above. Drill into these sediments, and you can measure changes in species, in grain size, in isotope ratios that track temperature and rainfall. In some lake cores from around the Indian Ocean and Southeast Asia, there is indeed a layer of Toba ash. Right above or within that ash, some records show hints of ecological disturbance, changes in the kinds of pollen that appear, shifts in indicators of lake level or salinity. In a few places there are suggestions of drier conditions or cooler surfaces for a short interval after the eruption. But again, it's not a uniform picture. In many records, the decades and centuries after Toba look stressed but not apocalyptic. Vegetation changes, but then recovers. Lake levels fluctuate, but don't drop off a cliff. In African records, the climate continues to wobble as part of longer glacial cycles, with wet and dry phases that don't line up neatly with a single global shutdown. To make sense of this patchwork, climate scientists turn to models. They take what we know about how much sulfur Toba likely pumped into the stratosphere, how big the ash cloud might have been, how high it rose. They plug those numbers into complex simulations of the atmosphere and oceans, the same types of models used to study modern climate change. Then they watch what happens. Some of these models, especially earlier ones, produce dramatic outcomes. Global average temperatures dropping 3, 4, even more degrees Celsius for several years, with long-lasting disruptions to monsoons and vegetation. In those scenarios, many regions, especially in the tropics and subtropics, would have seen sharply reduced rainfall, shorter growing seasons, and repeated crop failures if agriculture had existed. Later models, using refined inputs and better representations of how aerosols spread and fall out of the sky, often show milder effects, cooling perhaps on the order of 1 or 2 degrees globally, concentrated in the first couple of years, then tapering off as aerosols settle or are rained out. Some simulations show stronger impacts in certain regions, like weakened Indian and African monsoons, while others suggest that ocean dynamics and pre-existing climate patterns could have moderated the shock. Why the disagreement? Partly because we don't know exact numbers. We don't have a precise measurement of how much sulfur Toba released, how it interacted with clouds, how quickly particles clumped and fell. Small changes in those assumptions can produce large differences in the modelled outcome, and partly because global average temperature is a blunt tool. Imagine that the planet cools by, say, 1.5 degrees Celsius on average after Toba. That doesn't mean every place cools by 1.5 degrees. Some regions might cool by 4 or 5 degrees, others might barely notice. Some might even warm slightly in certain seasons because of shifting wind patterns. So when we talk about a volcanic winter, we have to be careful not to confuse global averages with local experience. In some parts of the world, especially downwind of the eruption or in sensitive monsoon belts, the aftermath of Toba might have felt like a genuine climatic shock. Dimmer skies, unseasonably cold seasons, failing rains, stressed vegetation. In other areas, the change might have been unpleasant but survivable, slightly cooler temperatures, some shifts in rainfall, but nothing that would necessarily wipe out human groups already adapted to variability. This is where habitability enters the story. A region can suffer a measurable temperature drop and still remain habitable for hunter-gatherers, especially if those people are mobile, knowledgeable about local resources, and able to adjust their hunting and foraging strategies. A 2-degree cooling might reduce certain plant yields, but leave coastal shellfish or underground tubers largely unaffected. A weaker monsoon could hurt large grazing animals, but might not entirely erase small game, fish or edible plants in microhabitats. So when scientists ask, did Toba cause a volcanic winter? They're really asking several questions at once. Did it inject enough aerosols to cool the Earth measurably? Almost certainly yes. Was that cooling globally catastrophic, driving ecosystems everywhere into collapse? The evidence so far says, probably not. Did some regions experience something close to a local or regional volcanic winter, with serious ecological stress lasting years to decades? Quite possibly. And were those stressed regions the same ones where early humans were living in large numbers? That's the question that keeps drawing researchers back to this story. Today, if we had to attach probabilities rather than proclamations, the picture might look like this. It's very likely that Toba caused a noticeable short-term global cooling on the scale of a few years to a decade, superimposed on an already cold, unstable Ice Age climate. It's quite plausible that in parts of South Asia, and perhaps parts of Africa, the climate shifts after Toba were severe enough to strain plant and animal communities, forcing human groups to move, shrink, or reorganize. It's less likely, though not impossible, that Toba alone produced a planet-wide, decades-long dark age that nearly exterminated our species in a single stroke. Instead, most researchers now see Toba as one heavy blow among many, a major eruption that dimmed the skies, chilled the air, and added stress to ecosystems already dealing with glacial rhythms, shifting coastlines, and changing rainfall patterns. For some human groups, especially those living close to the ashfall or relying on vulnerable food webs, the aftermath might have been devastating. For others in sheltered African refuges or along resilient coasts, the change might have been harsh but survivable. To find out which was which, we have to go down from the global view into specific landscapes. The river valleys and rock shelters of South Asia, the caves and coastlines of Africa, the places where Toba's ash still lies buried above stone tools and ancient hearths. That's where we'll go next. following the trail of ash and artifacts to see how real people in real places lived through one of the greatest eruptions in human time. Across much of South Asia, Toba is not an abstract event in a climate model. It is a thin, pale line in the ground, walk across parts of India, Pakistan, Bangladesh, even as far as the Arabian Sea, and beneath modern soils and fields there lies a horizon of volcanic ash, a blanket of microscopic glass shards and crystals, sometimes just a few centimetres thick, sometimes more. Geologists call it the youngest Toba tuff. To them it's like a timestamp burned into the landscape. Chemically, that ash is distinctive. Its mineral fingerprint matches the Toba caldera in Sumatra. The further you go from the volcano, the thinner and more diffuse the layer becomes, but its composition stays recognizable. It's the same eruption, the same dust cloud that once drifted across the sky, now resting silently in river terraces, lake beds, and ancient soils. For archaeologists, this is an extraordinary opportunity, because in some of those places that ash does not lie alone. It lies sandwiched between layers of human activity. Imagine a rock shelter in central India. Before Toba, people came here. They knapped stone tools, left behind broken flakes and finished points, dropped bits of charcoal from their fires. Over time, these remnants built up a modest archaeological layer. Then ash fell. It sifted through the air, settled on rocks and leaves, washed into low spots by rain. In that shelter, a thin sheet of volcanic dust accumulated, a light-coloured band now visible when you cut into the sediment. Above it, time continued. More people came. More stones were struck. New hearths were kindled. Today, when excavators carefully peel back those layers, they can see three things at once: the tools made before the ash itself, and the tools made after. If Toba had wiped humans from this region entirely, we might expect to find tools below the ash, then nothing above for thousands of years. A gap, a silence. That's not what many sites show. In several localities in India and nearby regions, the stone tool industries below and above the Toba ash look strikingly similar. The same basic flake technologies, the same styles of points and scrapers, the same overall signature of how people were shaping stone. Some researchers look at that and see continuity. They argue that human groups were there before the eruption, endured whatever followed, and continued their traditions afterward with no obvious break. The ash, in this view, is like a dusting of snow on a busy road. It slows traffic, maybe, but it doesn't erase the road or the travellers. Others are more cautious. Similar tools do not necessarily mean the same people. Stone technology can persist even when populations change, especially if newcomers learn from remnants of older traditions or reinvent similar solutions to similar problems. And dating these layers precisely is difficult. Radiometric dates have margins of error. Sediments can be disturbed by roots, burrowing animals, later human activity. So debates begin. One camp emphasizes resilience. They point to sites where the density of tools above and below the ash is comparable, where there is no obvious hiatus in occupation, and argue that at least some South Asian populations rode out the eruption in place. To them, the ash layer is a scar, not a death certificate. Another camp leans into discontinuity. They note places where the ash appears to cap a sequence of tools with no clear continuation afterward, or where dates from post-ash layers suggest a pause before reoccupation. In that reading, Toba and its aftermath may have depopulated certain areas, leaving empty landscapes later recolonized by survivors from elsewhere. And then there is the third possibility, that some of our associations are simply wrong. Ash does not always fall neatly across an undisturbed surface and stay where it lands. It can be reworked by wind and water, carried into new contexts long after the eruption. A flood can scoop older artifacts and younger ash together into a single mixed layer. A hillside can slump, sliding sediments from different periods into an untidy heap. When archaeologists find stone tools just below or just above an ash horizon, they have to ask a series of hard questions. Has this layer been disturbed? Are the tools truly in primary position, or have they been moved? Are the dates we're assigning to these layers anchored by multiple methods, or relying on a single uncertain measurement? Because tiny shifts in these answers can change the story. If the tools really do sit calmly on either side of an undisturbed ash sheet, that's strong evidence for local survival. If the sediment shows signs of reworking, or if the radiometric ages blur together, then our neat narrative can unravel. The ash might have arrived late, relative to the tools, or the tools might have been older than we think, buried deeper by chance. Even when the stratigraphy looks reliable, interpretation is not straightforward. Take continuity of tool traditions. Some researchers see the same general style of stoneworking above and below Toba and argue for uninterrupted cultural transmission. Others point out that Middle Stone Age style technologies can remain stable for long periods and across wide regions. So similarity might only mean that people, wherever they were coming from, faced similar constraints and preferences. Perhaps Toba pushed people into refuges, pockets of more favourable conditions along rivers, in upland forests or near coasts, where they huddled for a generation or two. Then, as climate and vegetation recovered, their descendants spread back into vacated territories, bringing their familiar tool traditions with them. Archaeologically, that could look very much like continuity, even if specific local lineages had disappeared for a time. Or perhaps some communities never left at all. They might have shifted their foraging ranges, changed the balance between hunting and gathering, focused more on resilient resources like roots, shellfish, or small game. Their stone tools, optimized for cutting and scraping, might hardly change, even as their diets and movement patterns did. And hovering over all of this is the possibility that our chronological anchors are slightly off. If the age of the ash at a given site is misestimated by a few thousand years, it might not mark Toba at all, but another, smaller eruption. All the human occupation above or below could belong to a different climatic phase entirely. In that case, we'd be telling elaborate survival stories about people who never actually saw the sky go dark from Toba. South Asia then becomes a case study in how complicated bottleneck claims really are. On the one hand, the widespread Toba ash shows that this region was directly touched by the eruption. The fallout isn't a rumour, it's a physical layer spread over hundreds of thousands of square kilometres. Any humans living there would have experienced days or weeks of ashfall and years of altered skies and stressed ecosystems. On the other hand, the archaeological record interwoven with that ash does not sing a single clear song of catastrophe. Instead, it hums with ambiguity. Some sequences hint at resilience and continuity. Others hint at disruption and abandonment. Still others are too mixed or too poorly dated to speak confidently at all. Rather than a simple picture of Toba wipes South Asia clean, then humans return, what emerges is a mosaic of possibilities. Local refuges where people survived in place, corridors they later used to expand, zones that may have emptied for a while, and the ever-present risk that our lines on the timeline are slightly skewed. This complexity matters, because if a region so heavily dusted by Toba's ash can show signs of both survival and stress, then the story of our species' bottleneck is unlikely to be the tale of one eruption, one winter, one near-death experience. It's more likely a tangled web of local crises and local solutions layered over long-term climatic swings. To follow that web further, we have to look beyond South Asia, back to the continent where our lineage first arose, and to the places that may have sheltered the ancestors who eventually gave rise to all of us, the refuges of Africa and the narrow coastal lifelines that might have carried humanity through the dark. When scientists talk about refuges, they don't mean cosy cabins or safe houses. They mean places where, in an otherwise hostile world, conditions were just good enough for life to hang on. In Ice Age Africa, that didn't mean tropical luxury. It meant valleys where a river still flowed when surrounding plains had dried to dust. It meant highland pockets where cooler temperatures trapped a little more rainfall. It meant strips of woodland that remained green when nearby hills browned and withered. And very often it meant coastlines. Across eastern and southern Africa, paleo-environmental records hint at these pockets of relative stability. While some regions swung violently between wet and dry, others show more muted fluctuations. Lake cores preserve layers of mud rich in pollen from plants that, like moisture, even during broader drought phases. Cave and rock shelter sediments hold fragments of charcoal, bone and ash that persist right through harsh climatic episodes. To many researchers, these are the fingerprints of refuges, places where human groups could retreat when the wider landscape turned against them, and from which they could expand again when conditions improved. The coasts in particular look like a lifeline, because even when inland ecosystems crash, the boundary between land and sea behaves differently. Tides still rise and fall. Waves still stir nutrients from the deep. Many shellfish, algae, and small coastal fish are relatively resilient to changes in rainfall and temperature on land. They may shift in abundance, but they don't vanish as quickly as herds of large mammals can during prolonged droughts. For hungry humans, that matters. A shoreline rich in mussels, limpets, oysters, crabs, and small fish offers something incredibly precious in a time of chaos: predictable calories. You don't have to chase shellfish over the horizon. You don't need to track migrations. You visit the rocky platforms or tidal pools when the tide is right, and the food is simply there. In southern Africa, sites like Pinnacle Point, Clayse's River, Blombo's Cave, and others preserve layers upon layers of these coastal lives. Thick accumulations of shells, fish bones and hearths show that people were exploiting marine resources deeply into the Middle Stone Age, well before 70,000 years ago, and continuing through periods when inland environments were stressed. These deposits are not just scraps of ancient dinners. They are records of planning. Gathering shellfish effectively means knowing the tidal cycle, when water will retreat, which rocks will be exposed, how long you have before the sea returns. It means learning which species are safe, which are poisonous, which are worth the effort to pry off the rocks. And because the tides follow the moon, it means recognizing patterns that repeat on a rhythm longer than a single day. You don't do that by accident. You do it by watching, remembering, and teaching. Now add something else: sea level. During glacial periods, when much of Earth's water was locked up in ice sheets, global sea level dropped, sometimes by more than 100 meters. The shorelines of Africa did not stay where they are today. They marched outward, exposing wide shelves of land that are now drowned. What would that have looked like from the ground? If you stood on a cliff in southern Africa 70,000 or 80,000 years ago, you might have seen a shoreline far out where the modern waves never reach, with long stretches of new coastal plain between you and the water. Rivers would have cut deeper channels as they ran across that exposed land. Estuaries and lagoons would have formed in low spots. New habitats, rich in fish, shellfish, birds and plant life, would have appeared. Those broad continental shelves could have been enormous foraging grounds, and, just as importantly, natural highways. A relatively flat, resource-rich coastal plain is easier to traverse than steep, broken interior mountains or hyper-arid deserts. With shellfish, fish, seabirds and coastal plants as dependable stops along the way, small human groups could move gradually along the edge of the continent without needing to solve the problem of food fresh at every step. Some researchers think this created what they call a coastal migration corridor, not just for the later expansion out of Africa, but internally within the continent itself. As climates swung back and forth, people might have shifted their ranges along these extended shorelines, tracking the band where conditions were best. There's a twist, though. Most of those ancient coastal camps and middens now sit underwater, buried beneath tens of meters of modern sea. We only glimpse the edges of that world where caves and shelters happen to lie just above today's shoreline, or where uplift and erosion have brought old surfaces back into view. Even those limited glimpses are revealing. At some coastal refuge sites dating to around the Bottleneck period, and earlier, archaeologists find more than shells and hearths. They find signs of symbolic behaviour, pieces of ochre ground smooth and engraved with cross-hatched patterns, drilled shells that may have been strung as beads, fragments of bone shaped into points and tools. At Blombos Cave, for instance, engraved ochre plaques and shell beads have been dated to around 70–75,000 years ago, perhaps a bit earlier. At other sites there are carefully selected and transported pigments and combinations of tools and ornaments that suggest more than purely practical concerns. These objects are not food. They do not keep you warm or cut your meat any better than plain stone. They are about meaning, about marking identity, belonging, status, or shared stories in a refuge setting that takes on added significance. When populations shrink and scatter, the risk is not just physical extinction. It's cultural erosion, stories can be lost, techniques can vanish if a single skilled individual dies without passing them on. Rituals and identities can dissolve if groups fragment beyond repair. Symbolic items, beads, pigments, engravings, may have helped hold people together when everything else was falling apart. They could mark who is us and who is them, encode clan or band affiliations, or serve as tangible links to ancestors and shared memories. They might also have smoothed interactions between groups who met at the edges of refuges, enabling exchange, marriage, and cooperation instead of conflict. And cooperation under bottleneck conditions is not an optional luxury. It is a survival technology. The coastal refuges also forced and rewarded complex planning, exploiting tides, scheduling trips to distant freshwater sources, coordinating group hunts for seals or large fish, perhaps even anticipating seasonal changes in storm patterns or upwelling currents that affected where fish would be plentiful. All of this selects for minds that can think ahead, share information, and imagine futures that have not yet happened. Those are the same cognitive qualities that underpin language, abstract thought, and sophisticated social systems. Meanwhile, inland refuges along large rivers like the Nile, in Ethiopian highlands, around long-lived lakes in East Africa, in pockets of forest, would have faced different but related challenges. Their resources were linked more tightly to rainfall and vegetation, but they too offered stability compared to the most arid zones. Genetic studies hint at long-standing population structure within Africa. Groups separated enough to develop distinct lineages, yet connected enough by occasional gene flow to remain part of one species. Refuges help explain that pattern. Even when the overall human population was small, it was not pressed into a single camp. Different pockets, coastal and inland, north and south, highland and lowland, could host their own small bands of survivors. When conditions briefly improved, these bands could grow and send out splinters. Those splinters might reach other refuges, mix with their inhabitants, and then retreat again when the next dry phase came. In this way, refuges acted as reservoirs not just of people, but of diversity, genetic diversity, because isolated groups could drift apart and adapt in slightly different ways before reconnecting. Cultural diversity, because different environments favoured different subsistence strategies, toolkits, and social traditions. When groups met, they didn't just exchange genes, they exchanged ideas about fishing, hunting, pigments, ornaments, stories. In a world of repeated stresses, that diversity was insurance. If one strategy failed in a new climatic twist, another might work. If one lineage was hit hard by disease or famine, others could repopulate the gap. So when we imagine the bottleneck, we shouldn't picture a single shrinking dot on a map. We should imagine a constellation of faint lights, some blinking out, others glowing on, connected by thin, flickering lines of movement and marriage and memory. Along Africa's rivers in its highland valleys, and especially along those now drowned coasts, those lights persisted. Small groups, holding to their shorelines and their stories, maintained enough people and enough variation that when the world finally eased its grip, humanity still had room to grow. But even as the coasts and refuges offered lifelines, other forces were still pressing in. Volcanoes were only one part of the pressure. Droughts, shifting monsoons, changing currents, and perhaps our own success as hunters were also reshaping the landscape of survival. To see the full weight that bore down on those scattered ancestors, we have to step back from the shore and look at the broader climate machine that governed their fate. When people first hear about the human bottleneck, they often look for one villain, a single explosion, a single winter, a single event that nearly erased us. But the more scientists study this period, the less it looks like a crime with one culprit, and the more it looks like a long, grinding siege. Not one hammer blow, but a constant uneven pounding from many directions at once. Start with the simplest and perhaps the cruelest, the drying of the land. Over and over across the last million years, Africa's climate flipped between greener, wetter phases and stark, arid ones. These weren't gentle swings, they were driven by changes in Earth's orbit, shifts in monsoon patterns, rearrangements of ocean currents. In the records of old lakes and dust blown across oceans, you can see these shifts like heartbeats, wet, dry, sometimes spaced only a few thousand years apart. For people whose lives depended on wild plants and animals, those pulses mattered. As rainfall retreated, grasslands shrank and woodlands withered. Rivers broke into disconnected pools, then into cracked mud. Plants that could once be gathered within a day's walk might suddenly be scattered across many days of desperate wandering. Animals that had once followed predictable grazing circuits might vanish entirely from a region or compress into shrinking oases where competition and danger were intense. In a world like that, even good years came with a shadow. Maybe the rains were strong for a decade, herds were plentiful, children were born and survived. But anyone old enough to remember would know it could change again. The stories told around fires would not be about stability. They would be about the last time the river failed, the last time the wind turned hot and the sky turned white with dust. This kind of chronic uncertainty is its own kind of pressure. You can live through one drought if you have fat reserves, stored food or neighbours to trade with. But when droughts return, again and again, when wet years are short and dry years are long, you never quite recover. Hunting grounds don't fully restock, fruit trees don't mature before the next failed rainy season. Children who survived the first hard spell may be weakened and more vulnerable to the next. Layered on top of this were invisible enemies, diseases and parasites shifting with the changing environment. As water sources shrank, humans and animals were squeezed closer together around what remained. Lakes, swamps and slow rivers became crowded bottlenecks of life. Those are exactly the kinds of places where parasites thrive. Mosquitoes breed in small pools. Snails that host blood flukes multiply in certain kinds of shallow, warm water. Fleas and ticks find many hosts when herds and predators and people share the same narrow corridors. Change the climate, and you often change the disease map. When formerly dry areas became briefly wet, new breeding grounds opened up. When once permanent wetlands dried, species that depended on them either adapted, shifted, or died out, sometimes carrying their parasites with them into new, more human-dense refuges. Our ancestors had no germ theory, but they would have noticed patterns. Certain valleys where people seemed to get sick more often. Certain seasons when fevers and wasting illnesses swept through camp after camp. Sudden deaths after drinking from a particular pool, or after biting insects returned with the rains. For small bands of foragers, disease didn't have to be a massive plague to be deadly at the population level. A few extra infant deaths per generation. A slightly higher chance that a pregnant woman dies of infection. A periodic fever that leaves hunters too weak to chase game in the crucial weeks before the dry season. These are not dramatic disasters, but over centuries, they quietly drain numbers and resilience. Then there were the ecological cascades, the slow unravelling of entire food webs. As the climate lurched back and forth, some plant communities couldn't keep up. Species that once anchored entire ecosystems declined or disappeared from certain regions. Trees that held soils in place died, and with them went shade, leaf litter, and the insects and birds that depended on them. Grasses that fed large herbivores receded, replaced by tougher shrubs or bare ground. When key plants vanish or thin out, the animals that eat them follow. Large herbivores are especially vulnerable. They need lots of food and water, and they usually breed slowly. A series of bad years can crash their populations. Once herds are small and scattered, predators, both four-legged and human, have a harder time finding them. A dry spell that kills off the weakest antelope doesn't just hurt the antelope, it also means fewer meals for the lions, hyenas, and people who rely on them. In some places, fire joined this dance. Dry grass and woody shrubs make good fuel. In arid phases, lightning strikes and human-set fires could spread more easily, burning wider areas more often. Some plants are adapted to fire and rebound quickly, others are not. Repeated burning can convert mixed woodland into more open scrub. That might help some grazing animals, but it could hurt fruit-bearing trees or tuber-producing plants that bands of humans depended on. Over thousands of years, these kinds of changes fragment habitats. Instead of continuous belts of good country, you get patches, a highland where the rain still falls, a river corridor that stays green, a patch of coastal plain where mist and upwelling keep plants alive. Between these patches, stretches of land become marginal, too dry, too barren, or too unpredictable to support permanent human groups. To move between refuges, our ancestors would have had to cross these marginal lands, timing their journeys to short windows when plants briefly greened up, or when a seasonal river held water. Sometimes they probably miscalculated. A journey that had been safe a few generations earlier might become a deadly gamble if the rains failed a little earlier than expected, or if a grassland had quietly turned to desert. When you add all of this up, drought cycles, disease shifts, prey decline, habitat fragmentation, changing fire regimes, you get something that can from a distance look like the effect of one massive disaster. Population genetics. Looking back through the lens of DNA, can see that numbers plunged. But genes don't record whether that plunge came from a comet, a supervolcano, or a long era of grinding, overlapping stress. Many researchers now think the bottleneck may have been less a single crash and more a long staircase downward, each step carved by a different combination of forces. A few hard droughts here, a disease outbreak there, a local prey collapse somewhere else. Any one of those might have been survivable in isolation. Together, recurring, interacting, they could push a species into a narrow funnel of survival. This matters because it changes how we imagine our ancestors' world. Instead of picturing them as the victims of one apocalyptic moment, we can see them as long-term survivors in a landscape that never fully settled. They weren't just recovering from Toba or from any one eruption. They were navigating a tapestry of risks, climate swings, ecological shifts, disease environments that continually reshaped where they could live and how they could make a living. And it's important to say, these ideas are not final verdicts. The exact mix of stresses that produce the human bottleneck is still debated. Some lines of evidence point more strongly to climate. Others emphasize ecological change or the effects of our own hunting. New fossil finds, better climate models, and more detailed genetic analyses are still refining the picture. What we can say is that a simple single-cause story no longer fits comfortably with the data. It looks more likely that our species was squeezed by many hands at once, over long stretches of time. That the near extinction was not a single storm, but a long, stormy season. And in that kind of world, something else becomes clear. If survival depended not just on withstanding one blow, but on enduring many, then the structure of human life, our small groups, our movements, our ways of sharing information, becomes even more central. To understand how 1,280 ancestors made it through that gauntlet, we have to zoom into their scale, to the risks and decisions of tiny bands scattered across a dangerous continent. That is where we turn next. Imagine one of those bands, maybe 20, 30 people, a few older adults, a cluster of brothers and sisters, a handful of children, 1 or 2 newborns, a core of people who have known each other since birth, plus a couple of in-laws who came from another group years ago carrying different stories, different songs. At that scale, the whole future of your band can turn on what, from a distance, just looks like luck. Demographers, the people who study populations, like to talk in big numbers. Thousands, millions, percentages and averages. But in a band of 30, even tiny random shifts can be enormous. If 3 women of childbearing age die in a short time, 1 from infection after birth, 1 from a fall, 1 from a snake bite, that might be 1/10 of your entire group and a much larger share of your future births. If over a decade there just happen to be more boys than girls born, or vice versa, that skew shapes the next generation's families, the possible marriages, the number of children who will exist 20 years from now. Even the timing matters. If good years happen when many women are pregnant or nursing, more babies survive, and those cohorts swell. If a severe drought hits when several infants are just weaning, a whole slice of that age class might disappear. A disease that mostly strikes toddlers doesn't have to kill many to leave a visible gap 10 years later, when there are fewer adolescents able to hunt, gather, and protect. When your total population is in the low thousands, scattered across a continent, these local accidents don't cancel out the way they do in large societies. They stack. One band has an unlucky generation, too many deaths, too few births, and quietly fades out. Another, living in a slightly better patch, with slightly better luck, has a run of healthy children and becomes a seed for future expansions. Over centuries, this rise and fall looks in the genetic record like a steady thinning. But on the ground, it would have been felt as a series of intimate tragedies and fortunate runs. Then there's the problem of who you can have those children with. Small, isolated bands face a basic genetic risk, inbreeding. If people mate mostly within a tiny circle of close relatives, harmful recessive genes are more likely to meet. Birth defects become more common. Some children don't survive infancy. Others live but with weaknesses that make it harder to cope with a harsh environment. Fragile bones, immune problems, developmental issues that compromise learning and coordination. For a few generations, a band can muddle through this. Humans are biologically robust in many ways. But over longer stretches, repeated close-kin unions can slowly sap a group's vitality. In the worst cases, a band already stressed by hunger or disease might simply not have enough healthy children to replace its adults. Here is where something very human makes a difference: social networks. Even in a fragmented, dangerous landscape, there is evidence that our ancestors did not live as completely sealed-off islands. Archaeologists find similar stone tool traditions spread across wide regions, suggesting bands were in contact, sharing ideas, and maybe members. Genetic studies show patterns of what looks like regular partner exchange between neighbouring groups. You can picture how this works. A young woman, when she comes of age, travels or is escorted to another band not too far away, where she marries in. A young man might do the same in the other direction. Over time, This flows genes across the landscape, mixing lineages, diluting the effects of inbreeding in any single group. It also creates obligations and alliances. If your sister is married into a band 2 days walk away, their problems start to feel like your problems. If they have a run of bad luck, poor hunting, a sudden illness, you may feel compelled to help. If you suffer a misfortune, you can call on them. This is not just sentiment. It's strategy, encoded as custom. Mobility and exchange turn scattered, fragile bands into something slightly more resilient than their numbers alone would suggest. Think about food in this system. Your band might rely heavily on one river valley, one stretch of woodland, one coastal strip. You know its seasons in exquisite detail. You know when the shellfish are fattest, when the tubers are safest to dig, when the antelope fawns are easiest to catch. But if that one patch fails you, if the river dries, if a fire burns too hot, if a disease wipes out a key prey animal, you need options. Mobility is one option. You can move. In a relatively empty world, bands could at least sometimes pick up and shift to a neighbouring valley, following half-forgotten paths remembered from grandparents' stories. Or they could extend their seasonal rounds, walking farther to reach a certain fruiting tree line, or a series of rock pools that hold water longer into the dry months. But moving blindly is dangerous. You don't know who already lives there, or what diseases and hazards exist. This is where exchange and information flow matter. If you meet another band at a seasonal gathering and trade meat for stone, or shell beads for ochre, you're not just swapping objects. You're also trading maps in words. They may tell you, that ridge is dry now, don't go there. Or there is still water 3 days to the east, but the people there are quick to anger, avoid them. Or last year the herds moved farther north. If you follow this ravine, you might find them. These are not trivial details. In a marginal environment, a rumour about a distant spring or a warning about a hostile group might spell the difference between a successful relocation and a doomed trek. Over time, these patterns of movement and exchange knit together what could have been isolated, doomed bands into a loose web that could flex under pressure. When one node broke, one band vanished. Others could expand into the gap. Migrants carried not only their genes, but also their skills and stories, into places where numbers had fallen. In this sense, culture itself behaves like a survival technology. We often think of technology as physical things, stone points, digging sticks, containers for water. But for a species like ours, whose minds and social lives are unusually complex, many of the most powerful survival tools are intangible. Ways of dividing meat so that every family gets enough, preventing resentment. Taboos about marrying too close a cousin, shaped by bitter experience of what happens when those rules are broken. Rites of passage that formalize exchanges between groups. Myths that encode warnings about certain valleys, certain winds, certain animals. Even simple rules of thumb: don't camp where the mosquitoes are thickest, burn old bedding to keep lice down, avoid stagnant pools after the first rains, act as cultural vaccines against threats no one understands in biochemical terms. You can see this in how knowledge was probably stored and transmitted. In a world without writing, information lives in people. In elders who remember the last great drought. In specialists who know how to make a particular adhesive or find a particular route. In storytellers who memorize long genealogies linking one band to another. Losing a few key individuals could mean losing whole chunks of adaptive knowledge. That's another kind of demographic fragility. Not just how many people you have, but which people. A band might look healthy by head count, but if it loses its best navigator, its most skilled healer, its only person who remembers the path to a critical dry season refuge, its real capacity to survive can be sharply reduced. Culture, in this sense, is always balanced on the edge of forgetting. When geneticists talk about a bottleneck, they're looking back through our DNA and seeing this fragility summed up in stark numbers. a minimum of perhaps 1,000 or so breeding individuals, maybe fewer, for a long stretch of time. It's tempting to turn that into a dramatic image, one tiny village clinging to life. But the reality, as far as we can tell, was more diffused and more precarious. Many small groups, some failing, some barely hanging on, a few thriving for a generation or two, accidents of birth ratios, strokes of weather, the chance presence of a good healer or skilled leader, the thickness of marriage ties to neighbouring bands, all quietly nudging lineages towards survival or oblivion. From far away, with the distance of tens of thousands of years, those nudges blur into a single number, a species passing through a narrow gate. But from the inside, it would have felt like constant local risk. Every birth, every journey, every dry season, a small wager placed against extinction. And yet, somewhere within that web of fragile bands and vulnerable children, changes were brewing. Because under that kind of pressure, in those tiny social worlds where every decision mattered, people were not just repeating old habits. They were also sometimes doing something new, experimenting with different ways of organising, sharing and thinking. Those experiments, multiplied across thousands of years and countless campsites, would slowly change what it meant to be human. That is the turning we turn to next. If you drop in on one of those campsites 40,000–50,000 years into the Bottleneck, much of what you'd see would feel deeply familiar across generations. People still napping stone, still roasting meat, still arguing quietly over who has done their share of work. But look more closely, and you begin to notice small shifts. The stones themselves are changing. For hundreds of thousands of years, human toolkits looked, in broad outline, remarkably conservative. Big, heavy hand axes, simple flakes knocked off a core. Useful, yes, but not subtle. During and after the Bottleneck period, the archaeological record starts to show something different. Flakes become smaller, thinner, more precise. Instead of one multi-purpose axe, you see series of specialized tools. Narrow points for piercing, scrapers for hide, backed blades with one sharp edge, and one dull edge for hafting. Hafting itself is a quiet revolution. Attaching a stone to a handle turns a sharp rock into a spear, a knife, a digging stick, a lever. But to do this well, you need more than muscle. You need an adhesive, something that will hold under strain and moisture and time. In several African sites from this period, there are traces of exactly that. Plant resins, tree gums mixed with powdered ochre or ash to change their properties, cooked carefully over fire to produce a sticky, durable glue. This is composite technology: stone, wood, fibre, resin. 4 different materials, each gathered in a different way, each with its own quirks, brought together into a single planned object. That kind of object doesn't just happen. Someone has to remember where the right trees grow, which season the sap runs best, how long to heat without burning, how to bind and dry and test. If they get it wrong, the spear point shears off inside a wounded animal and the band goes hungry. If they get it right, the same spear can be repaired and reused, passed from hand to hand. There's debate among researchers about exactly when and where these composite tools first became common. Some point to early examples in southern Africa more than 100,000 years ago. Others see later more decisive spreads in East Africa or the Levant. The pattern, though, is consistent. Over time, in multiple places, toolkits expand and become more modular, more flexible. The same quiet expansion seems to be happening in how people defended their own bodies against the climate. We have no fossilized shirts or trousers from this period. Leather and plant fibers rot, but the bones of small animals tell a suggestive story. In sites from the Bottleneck and its aftermath, there is a growing presence of animals that aren't especially rich in meat, but have valuable fur. Arctic fox, hare, certain small carnivores. Cut marks on their bones suggest the hides were carefully removed. Later, in colder regions, we find bone needles, tiny, with drilled eyes dated to tens of thousands of years ago. These are the fingerprints of sewing. Even before those needles appear, simpler awls and perforators hint at an earlier tradition of piercing and lacing hides. Clothing, once it exists in more than the most minimal form, changes where a band can live. A person wrapped in layered hides, fitted reasonably well, can sleep in cooler valleys, travel further into windy plateaus, stretch their hunting season. Crude windbreaks become tents, opportunistic shelters under rock overhangs become more deliberate constructions, with poles and coverings and, eventually, semi-permanent huts in particularly reliable spots. Fire, too, moves from being a comforting presence to something managed with increasing skill. Early humans almost certainly knew how to tend natural fire, carrying embers from lightning-struck trees, keeping coals alive in the ashes of a hearth. At some point, though, people begin reliably making fire on demand. The exact timing is contentious. Some argue for controlled fire deep in the past, others for more systematic mastery later. But in the bottleneck and post-bottleneck period, the evidence of repeated, well-placed hearths multiplies. Charcoal deposits suggest people were experimenting with deliberately burning vegetation to clear underbrush or encourage the growth of certain plants. Hearths appear in more marginal settings, high-altitude caves, exposed plains, where careful fuel use and wind protection would have been essential. Clothing, shelter, fire, together, they act almost like a second skin, an artificial climate that people carry with them. This extended body allows humans to push into zones that would once have been lethal. Colder nights, higher elevations, windier coasts. In a world of unstable rainfall and shifting ecosystems, that extra range is priceless. A band that can camp safely near a rich but chilly wetland, or endure a freak cold snap in an otherwise warm region, has options that their ancestors did not. And then there is the realm we cannot dig out of the ground, but which leaves shadows in beads and pigments and burials. Symbolism. Somewhere in this long, narrow corridor of our history, people begin to mark their own bodies, and perhaps their surroundings in ways that do not have an obvious practical function. Small shells drilled for stringing appear in South and North African sites. Pieces of ochre are not just scraped for pigment, but deliberately engraved with cross-hatchings and parallel lines. Later, carved figurines and complex burial arrangements join this growing record. Researchers argue about what these things mean. Some see them as early signs of personal ornamentation and group identity, ways of saying, I belong to this band, this clan, this story. Others are more cautious, noting that a few beads do not necessarily imply fully developed art in the modern sense. But at minimum, such objects show that people were investing time and care into things that communicated, however subtly, with other minds. When you can wear coded information on your body, colours, scars, hairstyles, pendants, you make social interactions more efficient. You can spot an ally, a potential marriage partner, a member of a trade network at a distance. You can signal your status, your role, your intentions before anyone speaks. And when you start to think in symbols, this colour for blood, that shape for a certain animal, this pattern for a lineage, your capacity for abstract thought deepens. You can plan, tell stories, remember obligations not just as feelings but as structured narratives. Language, which was surely evolving long before any surviving beads or engravings, finds a new playground in this symbolic environment. More things to name, more relationships to describe, more invisible concepts, promises, debts, totems, taboos, to pass on from mouth to ear. This doesn't mean there was a single global behavioural revolution when everyone suddenly became modern. The record doesn't support a clean break. Instead, there are regional blooms. In one period, southern Africa offers engraved ochre and long-distance shell exchange. In another, East Africa shows complex hunting strategies and finely made points. Later, Europe will explode with cave art and carved figurines. Different regions, different tempos, different emphases. What ties them together is not a date on a timeline, but a direction. Band by band, valley by valley, people are layering more and more culture between themselves and the rawness of the environment. Tools are becoming more adaptable. Clothing and shelter are buffering temperature and wind. Fire is reshaping landscapes and diets. Symbols and speech are coordinating larger, more reliable networks of cooperation. In a wildly unstable climate, this accumulation of small innovations acts like a shock absorber. A group that can switch prey because it has the right points and the right knowledge, that can move to a colder refuge because it has clothing and shelter skills, that can call on distant allies because it shares a language and symbolic system. That group can ride out fluctuations that might have shattered a less flexible way of life. Not every experiment succeeds. Some techniques are forgotten, some lines of ornament or ritual die with the bands that carried them. But across tens of thousands of years, the net effect is clear. Human behaviour is bending toward greater complexity, greater foresight, greater capacity to endure surprise. Those changes, slow and local as they felt at the time, are what prepared a tiny, bottlenecked species for what came next, not just surviving in Africa, but walking out of it. Out into Arabia, into Asia, into lands no human foot had ever touched. Those first steps out of Africa did not happen once like a single heroic march toward destiny. They happened in pulses. For a long time before the final successful expansion, small waves of humans had already tested the edges of their world. There are hints of our species in the Levant more than 100,000 years ago, teeth and tools that look tantalizingly like early Homo sapiens. These early explorers may have followed wetter corridors northward during brief climatic windows, when the Sahara shrank and greened, when rivers flowed where today there is only dust. Then the climate changed again. Deserts expanded. Forests and grasslands retreated. Those early excursions into Eurasia either died out or were swallowed back into Africa as populations shifted. Their traces are faint, like footprints on a beach that the tide has partially erased. 40,000 years later, another window opens. Around 70 to 60,000 years ago, a different combination of factors seems to align. Sea levels drop a little, narrowing the water between East Africa and Arabia. Parts of the Arabian Peninsula become more habitable, dotted with lakes and seasonal rivers. At the same time, some African populations, hardened by the bottleneck and armed with new technologies and social systems, are pressing out along coastlines and river valleys in search of opportunity. From this period, one particular movement stands out in the genetic record. A small group, perhaps just a few hundred breeding individuals, that left Africa and did not come back. This is what geneticists call the Out of Africa event, that gave rise to all non-African humans alive today. Everyone from indigenous Australians to ancient Europeans to First Nations in the Americas seems to trace part of their ancestry to this surprisingly tiny founding population. It's easy hearing this to confuse it with the bottleneck itself. Another frighteningly small number, another narrow pass in the story. But this time, the cause is different. When a tiny group leaves a larger population and successfully colonizes new territory, something called a founder effect kicks in. It's a kind of miniature bottleneck, but not necessarily driven by catastrophe. It's a filter created by geography and chance. Imagine a deck of cards representing the genetic diversity of Africa at that time. When a small band walks out across the Bab al-Mandeb straight into Arabia, they aren't carrying the whole deck with them. They carry a subset, some alleles, some lineages, some quirks of physiology and behaviour. Over generations, as their descendants spread and multiply across Eurasia, that limited sample becomes the foundation for an enormous population. Later, when geneticists look backward, they see a pattern, far less diversity outside Africa than within it, and a signature that looks very much like a population that has passed through a narrow gate. Without context, it can resemble a global near-death event. But on this scale, at this time, it is the familiar shape of colonization, a founder effect written large across continents. How exactly did those founders move? Here the story branches into two main paths, the coastal route and the inland corridors. In the coastal scenario, our ancestors, already skilled at exploiting shellfish, tidal pools and nearshore resources, slip along the shorelines. From the Horn of Africa to southern Arabia, then eastward along the margins of the Indian Ocean, Yemen, Oman, perhaps the coasts of Iran and Pakistan, the long curve of India onward to Southeast Asia, and much later, Australia. Supporting this view are early archaeological sites in South Asia with stone tools that look related to African traditions, and the presence of human populations in Australia by at least 65,000 years ago, maybe earlier. Moving quickly along coastlines, stopping in rich estuaries and bays, using boats or rafts to cross short stretches of water. It is plausible that small bands could have spread astonishing distances in just a few thousand years. The coast offers a kind of moving refuge, predictable tides, fish runs, shell beds, seabirds and driftwood for fires. For a species forged in the instability of the bottleneck, this string of relatively stable niches would have been deeply attractive. The inland corridor picture is different. In this view, humans push out of northeast Africa into the Sinai and Levant, or cross into Arabia and head inland along river valleys and seasonal lakes that bloom during wetter climatic phases. Paleolakes and buried river systems in the Arabian Peninsula, the Levantine corridor linking Africa to southwest Asia, and steppe-like environments stretching into Central Asia all become potential highways. There is supportive evidence here too. Stone tools scattered across now arid Arabian landscapes, fossils in the Levant that suggest repeated occupations, genetic signals that imply complex movements back and forth between Africa and Western Eurasia over tens of thousands of years. The two models are not enemies. They may both be right. A coastal band in one generation can give rise to inland foragers in the next, tracking herds into the interior during a run of good seasons. An inland group can, in turn, drift back toward the coasts when the rivers dry and the game thins. Over many centuries, genes and ideas spill back and forth between shoreline and heartland, braiding routes that our simple maps struggle to capture. What does seem clear is the tempo. Once the constraint loosened, once that one successful founding population broke away and began moving, expansion was rapid. On geological timescales, it is a sprint. Within perhaps 5,000 to 10,000 years, humans are present from the eastern Mediterranean to India. Within another 10 or 20,000, they push into Southeast Asia and Australia. Later pulses drive north and west into Europe, and much later still, across the Bering Land Bridge into the Americas. This is what often happens after a long period of constraint, whether the constraint is environmental, demographic, or cultural. Pressure builds silently. Skills accumulate, social networks knit together, ready to funnel information and support. Then, when an opening appears, slightly lower sea levels, a wetter corridor, fewer competitors in a neighbouring region, the response is not tentative. It is explosive. The earlier, deeper bottleneck had already honed our species' capacity to take advantage of such openings. Populations that had learned to survive in stark refuges could rapidly fill richer landscapes when they encountered them. Technologies like composite tools and controlled fire made new territories more accessible. Symbolic communication and language made it easier to coordinate moves, scout ahead, and maintain ties with those left behind. From one angle, the story of Out of Africa looks like a series of small bands wandering into new lands. From another, it's the aftershock of that ancient bottleneck rippling outward. The genetic narrowness we see in non-African populations today is not just a shadow of past danger, but also a trace of past opportunity seized by a very small number of people at just the right time, on just the right routes. Africa remains the deep reservoir in this story, the place with the greatest genetic diversity, the longest continuous human presence. The bottleneck was likely centered there. Many migrations stayed there. Many lineages never left, but the question of whether there was a sharp global bottleneck around 70,000 years ago cannot really be separated from this wider dance of movement. Founder effects from migrations, local crashes and recoveries in different regions, and that older, more severe constriction hundreds of thousands of years earlier all layer together. What we call the bottleneck is one contour in a much larger landscape of expansions and contractions, departures and returns. And as those early travellers stepped into Arabia and beyond, they were not walking into an empty stage. Other humans were already there, shaped by their own histories, carrying their own traces of the ancient crisis. The next chapter in the story is not just about movement, but about meetings. When our ancestors looked out across the headlands of Arabia or the plains of Western Asia, they were not seeing a virgin world. They were arriving in neighbourhoods already occupied, for at least 100,000 years before that decisive wave of Homo sapiens left Africa. Other humans had been living in Eurasia and adapting to its moods. The best known are the Neanderthals in Europe and Western Asia, and the more shadowy Denisovans farther east. There were probably others as well, late surviving Homo erectus, maybe small, isolated groups we haven't even named yet, known only as faint genetic whispers. To us, looking backward, it's tempting to draw clear lines. Sapiens here, Neanderthals there, Denisovans over yonder. 3 species, 3 territories, 3 destinies. The reality was much blurrier. Think instead of overlapping ranges like the territories of wolves, foxes and jackals. Sometimes separate, sometimes interwoven along river valleys, mountain passes and coasts. Each with its own history, its own toolkit, its own way of making a living. When modern humans first stepped into these regions, they were not pioneers in an empty land. They were walking into someone else's home. So, what happens when different kinds of humans meet? For a long time, the default story was simple and dramatic. We replaced them. Smarter, more flexible, armed with language and art, Homo sapiens poured out of Africa and swept the board, driving Neanderthals and Denisovans to extinction. But our DNA tells a softer, stranger story. When geneticists first sequenced the Neanderthal genome in the early 21st century, they were looking for differences, what made us different from them. What they found, almost by accident, was Neanderthal DNA inside living people. If you have ancestry from Europe, the Middle East, or much of Asia, somewhere between about 1 and 2% of your genome probably traces back to Neanderthals. People with roots in parts of East Asia can carry a bit more. Indigenous Australians, Papuans, and some Southeast Asian groups also carry DNA from Denisovans, sometimes in surprisingly high amounts. This is called introgression, genetic material from one population or species flowing into another through interbreeding. It means that meetings between sapiens and these archaic humans did not always end in conflict or avoidance. They also ended in sex, and in children who survived. Not just once, but multiple times. The patterns we see in genomes today suggest repeated episodes of contact. A group of modern humans meets Neanderthals in the Levant, mixes a little, then moves on. Another group encounters Neanderthals again somewhere in Central Asia or in Europe, hundreds or thousands of years later. Farther east, modern humans run into Denisovan populations more than once, picking up different sets of genes in different places. These weren't necessarily grand romances or peaceful fusions of cultures. Some encounters may have been violent, others perhaps were forged through trade or through captured or exchanged mates, or through small gradual infiltrations between neighbouring camps. Whatever their social form, they had a lasting biological effect. When a population has passed through a bottleneck, its genetic diversity is constrained. Some variants are lost forever, simply because there weren't enough people to carry them through. Others become common, not because they're good, but because of luck during those thin generations. Interbreeding with other humans is one way to refill that genetic reservoir. Imagine your ancestors carrying a narrow bundle of genes out of Africa, the limited deck of cards left to them by the ancient crisis and the more recent founder effect. Now imagine meeting Neanderthals, who had been evolving in cold Eurasian climates for hundreds of thousands of years, accumulating their own solutions, variants affecting skin and hair, immunity, maybe fat metabolism and circadian rhythms. Some of those Neanderthal genes, when introduced into a sapiens population, turned out to be useless or even harmful. Many were pruned away by natural selection, but some were immediately helpful. We see Neanderthal-derived alleles in modern immune system genes, for example, suggesting that interbreeding helped our ancestors cope with unfamiliar Eurasian pathogens. We find Denisovan variants in high-altitude populations of Tibet and the Himalayas, crucial for living in thin air. Other archaic genes seem to affect how our bodies respond to UV radiation, temperature and diet. In a sense, archaic humans became part of the toolkit that let Homo sapiens thrive in new environments. From that perspective, meeting the neighbours after a bottleneck isn't just a social event. It's a biological opportunity, a way for a recovering species to borrow adaptations it hasn't had time to evolve on its own. Of course, this picture is still under construction. We don't know exactly when the major episodes of interbreeding happened. Genetic estimates give ranges, perhaps around 50 to 60,000 years ago for some Neanderthal introgression, different windows for different Denisovan mixes, but these are averages smeared across time. A single encounter might have involved a handful of individuals over a few generations. Others might have involved intermittent contact over centuries. We also don't know precisely where many of these events unfolded. The Levant is a likely hotspot, because we have fossils of both sapiens and Neanderthals there. Central and Western Asia are strong candidates too, as are parts of Southeast Asia for Denisovans. But large swaths of the ancient map remain blank. Climate, erosion, and the randomness of discovery mean that entire chapters of this story may be buried under deserts, drowned on continental shelves, or ground to dust by glaciers. There are even hints of ghost populations, archaic humans who contributed DNA to modern people, but have left no clear fossils we can match to their genomes. Their signatures show up as odd stretches of sequence that don't quite fit Neanderthals, don't quite fit Denisovans, and don't look like any known modern human variation. These ghosts remind us that what we call Neanderthal or Denisovan might only be the visible peaks of a much more jagged landscape of ancient diversity. All of this complicates the comforting drama of a single apocalyptic bottleneck, followed by a clean, heroic comeback. Instead, we see a world in which different human populations, some coming out of severe crashes, some expanding in local refuges, some long established in Eurasia, overlap, mix, and replace each other in patchwork fashion. In one region, an archaic group might dwindle slowly, its last members absorbed into incoming sapiens bands. In another, modern human pioneers might fail, leaving Neanderthals or Denisovans dominant for thousands more years. In still another, people might shuttle back and forth, sharing tools, genes, and perhaps stories. The genetic signatures we interpret as the bottleneck are layered on top of this messiness. A deep, ancient constriction hundreds of thousands of years ago. Smaller, regional crashes triggered by climate swings or volcanic events like Toba. Repeated founder effects as small bands set out into new territories. And on top of it all, introgression, the quiet weaving together of lineages that had been separated for ages. When we talk about humanity, almost going extinct 70,000 years ago, it's worth keeping this braided history in mind. Our survival was not the tale of a single isolated group of sapiens heroically outlasting disaster and then replacing all others. It was part of a wider tapestry of humans meeting other humans, some like us, some not quite like us, and sharing, sometimes willingly, sometimes not, the very genes that would carry our line forward. Even at the edge of extinction, we were never entirely alone, and as these intertwined populations navigated ice and desert, volcano and sea, the lessons of survival, genetic, cultural and social, were accumulating. The question that remains is why, in the end, only one branch of this tangled family tree survived as a distinct species. Why did Neanderthals and Denisovans disappear as recognizable groups, even as their DNA lived on inside us? To explore that, we have to step back from the brink itself and look at what the bottleneck, and everything that followed, can teach us about what it means for a species to almost die and then drift forward into the future. When scientists talk about the bottleneck, they're not all talking about exactly the same thing. Some are focused on a deep ancient constriction in our lineage hundreds of thousands of years ago, like the one we walked through earlier in this story. Others are talking about a shallower, more recent squeeze somewhere around 70,000 years ago. Still others are looking at a pattern that isn't a single hourglass at all, but a series of narrowings, crashes and recoveries laid one on top of another. If you picture it as one dramatic night when the species almost ended, reality starts to fight back. If you picture it as a long, uneven twilight, stretched across continents and tens of thousands of years, the evidence starts to line up. One family of explanations puts the Toba supereruption at the centre of that twilight. In this view, a massive volcanic event in Sumatra throws ash and sulphur into the atmosphere, dimming sunlight and disrupting climate. Monsoons weaken, rainfall patterns stumble, plant communities shift. Directly underneath the ash cloud, ecosystems are hammered. Farther away, the damage ripples out through food chains and weather systems. Under this Toba-driven scenario, human populations that were already living close to the edge are pushed over it. Some groups vanish entirely, others shrink to a fraction of their former size. In genetic models, this looks like a sharp dip in population size followed by slow recovery. But even the strongest versions of the Toba hypothesis rarely claim that the entire species was reduced to a few thousand people overnight. Instead, they imagine regional collapses, staggered in time and space with some refuges escaping the worst of the fallout. Another camp leans away from volcanoes and toward climate. In this climate-driven picture, the big story is the unstable Ice Age itself. Long before and long after Toba, Earth's climate was lurching from colder to warmer, wetter to drier, in quirky, region-specific ways. Sea levels rose and fell. Grasslands turned to desert, then back to grassland. Forests advanced, retreated, and changed character. For hunter-gatherers living without agriculture, these shifts translate directly into feast and famine. A drying corridor can sever migration routes for animals. A changing coastline can drown rich shellfish beds that supported coastal bands. Glaciers advancing in high latitudes can block passes and redirect rivers, isolating some groups and forcing others to move. In this view, the bottleneck isn't one disaster, but the cumulative effect of many climatic swings, especially a harsh stretch around 70,000 years ago. Some regions become demographic dead zones. Others shrink into marginal refuges with just enough resources to support small, mobile groups. A third perspective says, why not both and more? Multi-cause models treat the bottleneck as the overlapping result of volcanism, climate, disease, competition, and plain old demographic bad luck. Maybe Toba did knock down some populations in South Asia. Maybe at about the same time, other regions were being stressed by droughts or cooling trends, that had nothing to do with the volcano. Maybe new pathogens were moving along animal migration routes, hitting scattered bands with epidemics they had no immunity against. Maybe encounters with other humans, Neanderthals, Denisovans, or yet unidentified groups, sometimes ended in conflict and local population losses. Layer these together over a few thousand years, and the genetic signal you get might look like one big bottleneck, even if it was actually a patchwork of smaller crashes. And then there are the model-driven explanations. Geneticists often talk about effective population size, the number of breeding individuals that best explains the amount of genetic variation we see today. That number is not the same as the head count of people actually alive at a given moment. It's a kind of mathematical shorthand, compressing a messy history into a single curve. If a small number of bands contribute disproportionately to future generations because others die out, or because some lineages simply don't leave descendants, that alone can make effective population size sag, even without a single dramatic catastrophe. Founder effects matter too. Every time a small group splits off and pioneers a new region, it carries only a subset of the genetic diversity from its parent population. Repeated waves of dispersal can mimic the genetic signature of a bottleneck, even if the global census never drops as low as the models suggest. This is why different datasets point to different magnitudes and dates. Genomes from modern humans might emphasize long-term trends and deep constrictions. Mitochondrial DNA, passed down the maternal line, can spotlight one set of events. Y chromosomes passed down the paternal line can emphasize another. Ancient DNA from Neanderthals and Denisovans gives us snapshots at particular times and places, but those snapshots are patchy, biased toward cooler climates where DNA survives. Archaeological layers tell yet another story. Some sites show continuity across the supposed bottleneck period, similar tools, similar occupation patterns before and after Toba's ash. Others show gaps, breaks, or abrupt changes that might mark local crashes or migrations. And climate records from ice cores, marine sediments, pollen preserved in lakes add their own timelines, with their own uncertainties in dating and resolution. When scientists line all these up, they don't click together like a perfect jigsaw puzzle. They overlap, disagree, and leave holes. What's widely accepted is this: our species and our broader lineage have passed through severe demographic contractions. At several points, the number of breeding humans on Earth was far, far lower than it is today. Genetic diversity was pruned, sometimes harshly. We did not expand in a smooth, steady climb from a large, stable ancestral population. What remains debated is the exact timing, depth, and cause of each squeeze. Was there a single terrifying low point around 70,000 years ago when numbers dipped to a few thousand or even a few hundred? Or was that just one of several rough passages, some earlier, some later, some affecting only parts of Africa or Eurasia? Was Toba a major driver, a minor insult layered onto a bad climate run, or a local catastrophe whose broader impact has been overstated? Those questions are still open, and new data shifts the balance every few years. But whatever shape you give the bottleneck, one lesson stands out: resilience. The humans who navigated these narrow corridors of survival relied on a handful of strategies that appear again and again. Refuges, small pockets of habitable land where water, food, and shelter held out, even when the wider region failed. Rift valleys and highland lakes, wet tropical forests and stable spring systems. Sheltered coasts where shellfish, seaweed, and fish buffered the ups and downs of inland game. Mobility, the ability to move when things went bad, to follow shifting herds, new shorelines, and changing rainfall belts, to abandon a dying valley and gamble on a distant mountain range based on a rumour carried by a visiting hunter or a remembered story from a grandparent. Cooperation. Nobody crosses a bottleneck alone. Sharing food, tools, mates, and information within and between bands increases the odds that at least some lineages make it through. Trade networks for stone, shells, pigments, or meat are not just economic systems, they're lifelines spreading risk across space. Innovation, new ways of making tools, processing plants, storing food, and using fire allow small groups to squeeze more life out of marginal environments. Symbolic thinking and language help preserve and transmit hard-earned knowledge, so that one bad year doesn't erase an entire skill set. These are the traits that flicker in the archaeological record and glow in our reconstructed genomes. They also form the quiet moral of the Bottleneck story. We are here not because our ancestors lived in a stable, generous world, but because they didn't and still found ways to adapt. If you'd like to drift deeper into that long, fragile history, there's a full book version of this story waiting for you at sleepytimehistory.com. It unfolds these same themes: volcanoes, ice, wandering bands, and unlikely survivors at a slower pace, and there's a discount running there this week if you want to explore more while you rest. For now, it's enough to hold on to this. Whatever exact mix of volcano, climate, chance, and movement lies behind the bottleneck, it did not break us. It pared us down. It rearranged our family tree. It fused chromosomes, shuffled genes, and forced experiments in culture and cooperation. And from that narrow, precarious base, our species began the long, slow drift forward, out of refuges across continents, into the tangled future where you and I now lie, thinking about people who almost did not live long enough to become our ancestors. On the other side of the bottleneck, the world was still dangerous. The ice still advanced and retreated. Other humans still walked the earth. But something fundamental had shifted in us. To see what that meant for the millennia that followed, we have to follow those survivors as they stepped away from the brink and carried their fragile inheritance into time. So where does that leave us? Drifting here at the wide end of the bottleneck, trying to reconstruct a night we never saw. We started with a simple, unsettling question. Were there really moments when our entire species was reduced to just a few thousand people or fewer? The most cautious answer is, something like that almost certainly happened, more than once. Genetic evidence tells us our lineage has been squeezed hard. Not a gentle dip, but real constrictions, when the pool of ancestors shrank and many possible futures went dark. The archaeological record tells us that around 70,000 years ago, and in the long ages before and after, humans were living through climates and landscapes that shifted under their feet. Whether one of those constrictions lines up neatly with Toba's ash, or spreads instead across a longer, messier stretch of cold, drought, and bad luck, is still an open question. Toba might have been a major blow, a regional disaster that pushed already stressed populations over the edge in South Asia. Or it might have been one difficult chapter in a much longer story of unstable Ice Age climate, local crashes, and stepwise migrations. Founder effects, unequal survival between bands, and random demographic swings could have deepened the genetic signal without a single apocalyptic night. And the deeper, earlier bottlenecks, the ones that may have shaped the split between our species, Neanderthals and Denisovans, add another layer of uncertainty. Those events are even further away, written in older genes and sparser fossils. So, instead of one clean story, we have overlapping possibilities. A volcano-centered model in which ash and sulfur dim the skies and thin the herds. A climate-driven model in which ice sheets, shifting monsoons, and wandering deserts do the slow, grinding work of pruning populations. A multi-cause model that says it was never just one thing. It was always a tangle. Right now, the tangle is the most honest picture we have. Tomorrow it may look different. Every few years, a new ancient genome is sequenced from a tooth or finger bone in a cave. A new lake core is drilled, bringing up a timeline of pollen and dust that refines our map of past climates. A new archaeological site is dated more precisely, tightening or loosening the link between a layer of ash and a scatter of stone tools. Each new line of evidence nudges the curves on our graphs. Bottlenecks deepen or soften. Dates slide a little earlier or later. Sometimes a cherished hypothesis is quietly set aside. Sometimes a once marginal idea gains strength. This is part of what makes deep prehistory such a strangely soothing place to rest your mind. The story is vast, the stakes for us are real, but no single paper or discovery will ever settle it completely. We know enough to see the outline. We will never know enough to fill in every face. And yet one thread holds from start to finish. Whoever those surviving bands were, scattered along African coasts, clinging to rift lakes, edging through forests and savannas altered by ice and fire, they carried forward a fragile inheritance, language, memory, fire, cooperation, and a handful of fortunate genes. They didn't know they were passing through a bottleneck. They didn't know they were almost everyone's ancestors. They were simply trying to keep children alive through bad seasons and find enough to eat when the landscape shifted again. You are one of the outcomes of those attempts. If you'd like to sink deeper into that long, uncertain story, there's a full book about these prehistoric secrets waiting for you at sleepytimehistory.com. It takes the same questions about bottlenecks, volcanoes, ice, and wandering humans, and unfolds them slowly, with more room for side paths and strange details. You can read more there, and if you'd like to own it, you can buy it directly from the site. Before you drift off completely, if this helped you relax or gave you something gentle to think about, it really does help if you tap like, subscribe to the channel and leave a comment. Tell me where you're listening from tonight, what city, what country, or just from the dark under a blanket. And if you feel like it, which part of this journey through the bottleneck stayed with you? Those small signals help this quiet kind of history find its way to more people trying to sleep. For now, just remember, our story bends through narrow places, but it keeps going. We have been at the brink before, and somehow, again and again, we drift forward. So, like, comment, and subscribe if you'd like to follow more of that drift, and share where in the world you're listening from, as you let the deep past carry you towards sleep.